Welcome back to my channel. So in the previous lectures we have seen NumPy, array operations, all of that. Now today we are going to look into the statistical part of the NumPy, where we are going to discuss about different distributions that are there and how do we actually use them, how do we import them. So we would be considering all of them. I will put up a box or the list of things that I'm going to cover in this lecture. Okay, so soon let's get started. The first operation that we are going to see is random. Random means something that cannot be predicted logically. Okay, random is not just a different number. It is something that you should not be able to predict with some logic. That is what a random number is like. Okay, so there are two types of random. One is pseudo random and another one is truly random. What is the difference between pseudo random and truly random? Pseudo random is a function that generates random numbers, which means there is a logic to generate random numbers. Okay, so for example, I'm defining a function where the first time it will just print something like increment of 2, the next time it will print like 2 plus 1, next time it will print like 3 plus 2. So I'm putting this logic to generate my next set of numbers, which means there is a logic that I could build to actually generate the random numbers. So this is called as a pseudo random number. So the next thing is truly random number. What is the difference between this both? Truly random number is based on the mouse clip or some kind of a random data. Okay, for example, you are making a mouse shake and there should be some kind of coordinate changes that's happening within the mouse, right? So you could pick that number and make it as a random number and print it in your screen. So that way what happens is it becomes completely random and you don't have any logic to actually predict the number. So this is the difference between truly random and pseudo random. This is much important for you to understand. Okay, so when do we use what? Truly random. For example, in case of security risks where there are things like it has to be much secure, in that case they will rely on this truly random, where they will put some random number based on some random mouse click or some kind of a data that is present on the network that is totally irrelevant. So that the password or the security becomes much harder for the user to actually crack it. Okay, so the next is let's see how do we actually install this. Like same pip install numpy. Next is import numpy as numpy. Okay, this is all. Next is generating a random number. So random.rand int. Okay, this is the function which generates a random number, which means the random number will be within 100. Okay, it generates a random number between 100. Next is I'm printing it, I'm getting 43. The next time when I execute the same, I will have a different number that is actually getting coming here. Okay, next is random.rand, which is a float operation. Here if you see, we have mentioned the int, but here it's a float operation, which means it will be between 0 to 1. If here we are getting 0.6. Next is find numbers from the array. I need to generate between 1 to 100, but I need 5 numbers, which means it will return a list of 5 numbers consisting of 1 to 100, which will be of random numbers. Okay, next is 2D array of 3 rows and 5 columns. Here I have 3 rows and 5 columns, which means 5 values. Okay, so I'm generating between 100, which is going to be an integer. Same way. Next is choice. Out of 3, 5, 7, 9, randomly choose one. Okay, randomly choose one element, not one number, one element, which means here I am picking 5. For the next time when I run the same snippet of code, it might pick some other number randomly. Okay, next is 2D array with the following values of specific size. Random.choice is equal to 3, 5, 7, 9, 3, 5. Okay, the choice has to pick it has to generate a 3 into 5 matrix. Okay, 3 into 5 matrix where the data will be only from these 4 numbers. It should not have anything other than 4 numbers. That is what you see here as an output. Next is random data distribution. 1D array containing 100 values where each value has to be 1 to 17 or 186. So I was 1 to 17 or 186 is defined. 0.1, 0.3, 0.6, 0.0. Together if you sum up this, you will get a value of 1 because the probability. Okay, sum of all the probability of the numbers should be 1. Okay, next is size is equal to 100, which means it has to return me as 100 numbers. Okay, we can see that the generated numbers are present here, which means these generated numbers I have taken account of it for you to explain. 0.1 maps to 1, 0.3 maps to 2, 0.6 maps to 17. Okay, so if you see the number of 17, the number of elements, which is like 17, occurs the most of the times as it has the highest weightage. Okay, the second most fastest number is 2 because it comes most of the times, which is 23. Next is 14. That is the next. But if you see, this number 186 is totally missed because it has been assigned with 0. Okay, this is what random data distribution is. Next is count of the occurrence of numbers, which means, okay, this is something I have explained. Next is permute and shuffle. Okay, what is meant by permutation? What is shuffling? Okay, shuffling is basically like we have a set of cards, and before actually giving it to other people, we used to shuffle it, right? That is what shuffling is. And permute is a different format with the same set of numbers is what permute is. Okay, so shuffle makes changes to the original array. Okay, but permute does not make any changes to the original array, leaves the original array unchanged, but rearranges the actual only the array that gets permuted. Okay, so how do I apply that function? Put dot shuffle to get the shuffled array, dot permutation to get the permutation of the array. Okay, it is very necessary that you have to understand the differences of this function, even though the whatever the results that you see is different, the actual internal implementation is a little different. Okay, next is Seaborn and Matplotlib. So Matplotlib is basically used for plotting the graphs, all of them. Seaborn is also for the same purpose it is being used. So sns.displot, if I just give this numbers, it will just give me a plot. I think, yeah, here is a plot. Okay, so if you see here, the number that that is given is 0, 1, 2, 3, 4, 5. Okay, so it just has given me starting from 0. It has given 1, 2, 3, 4, 5, which is actually the given input that we have, which it gave the graph. Okay, next is without histogram. What is a histogram? Histogram helps us to understand the frequency of the numerical data using rectangles. Okay, if you see here, this is with histogram, but here we are totally removing histogram by mentioning that the histogram parameter as false. Okay, by this you can just get a trend analysis or line chart, that is sufficient. Next is Gaussian distribution. There are different types of distribution: Gaussian distribution, nominal, multinomial. There are a lot of them. Let's discuss them one by one here. Okay, please give a lot of attention to this one because these are also a little bit of statistics which is coming in. So let's get started. If you see here, what is a Gaussian or a normal distribution? You might have learned this in college days. During your engineering times. Okay, it is characterized by a bell-shaped curve where most values cluster around the mean. What is a mean? Okay, if you have 1, 2, 3, if you just add this, you will get 6. There are 3 numbers, so 6 by 3, 1 by 2. What is the mean of these numbers? Is 2, which means basically a average of the set of numbers. Okay, where most values cluster around the mean, and the further away you move the mean, the fewer you encounter. Okay, which means as long as you move away from the mean, the number of data points will be little less is what is being told here. Okay, that is how you get a bell-shaped curve as you see here. Okay, imagine you are measuring the heights of students in a classroom. If most students are around the average height, with only a few being significantly taller or shorter, their heights would follow a Gaussian distribution. It's a handy mathematical model for describing how data is spread out around the central value. Okay, how data is spread out around the central value. From the central value, how is the data actually spread out is what it helps us to understand. How do you apply it? X is equal to random dot normal, which is basically a normal distribution. This is also called as a Gaussian distribution, right? So size is equal to 2 into 3, which means 2 into 3 means it must give me a matrix of size 2 into 3. That is what it means. You can see the values as 2 into 3 here, and we have parameters apart from size. One is LOC, which is a mean where the peak of the bell exists, and another one is the scale, which is the standard deviation, how flat the graph distribution should be. Okay, so I have mentioned the mean to be 1 and the scale to be 2, which means this is mean and this is standard deviation, and the returned array should be 2, 3. So that is what you see as an output here. Okay, so what does each value in this mean? Each value represents a random observation drawn from normal distribution with a mean of 1, which means with a mean of 1 that we have mentioned here, and a standard deviation of 2. Okay, and the standard deviation of 2. Next is the mean of the distribution is shifted to 1, so the values tend to be closer to the average. Okay, the mean of the distribution, which means mentioned here, is shifted to 1, so the values tend to be closer to 1 on average. Okay, next is the standard deviation of 2 determines how spread out the values are around the mean. Larger the standard deviation values results in wider spread of the values, which basically means, for example, assume you have a graph here, you got something like this. Okay, which means you have a which means the spread is very long, the standard deviation is very long. Assume you have a bell shape, like you have a graph like this and you have something like this, which means the standard deviation is very short. So that is what they mean here. Next is discrete distribution versus continuous distribution. Okay, so what are discrete values and what are continuous values? We have to understand it before we move to binomial distribution, so that it's much easier for you to understand when you move to the next topics. What is discrete? Okay, represents probabilities of outcomes in a finite or countable infinite set of possible values. Okay, discrete means individual. Okay, individual values. Example including rolling a dice, counting the occurrence of words in a text, recording the number of defects in a batch of products. Okay, so possible outcomes could be, for example, you roll a dice, what are the values that you could see? 1, 2, 3, 4, 5, 6, and not more than that, right? Which means the possible outcomes are 6. Next is continuous distribution, represents probabilities of outcomes in a continuous range of values, where the value of the ranges is continuous. For example, take today the Bangalore city has a temperature of some 23 degrees Celsius, and tomorrow it's going to be 25 degrees Celsius. Somewhere between this range, it will be anything, right? So it is continuous, 23.1 to it could be anything. So it is a continuous range and it is not a discrete value. Okay, that is what they mean by discrete, continuous distribution and discrete distribution. Okay, next let's move to binomial distribution. Binomial, okay, this is a discrete type of distribution. What is discrete? We have seen here, we have individual values, which means like a rolling a dice is called. Okay, outcome of binary scenarios. Example, toss of a coin, it will either be head or false. For example, there is a boolean variable, it will be only something like true or false, right? So it is binomial in nature. Same way, toss of a coin, it should be either tail or it should be either tail or heads. Okay, so outcome is a binary scenario. Binary refers to actually 0 and 1, which means two things. 0 means false, 1 means true. Okay, here toss of a coin, head or tails. So number of trials, which means n. P is the probability of occurrence of each trial. Example, what? For toss of a coin, 0.5 each. Okay, so what is the probability when you toss a coin that it will have, what is the toss will come? It is half, right? 1 by 2. If there are two options, 1 by 2, which means is equal to 0.5. That is what they have mentioned. Toss of a coin to be something is 0.5 each. Okay, that is what binomial distribution is. How do you apply it? Binomial, number of trials is equal to 10, P is equal to 0.5, which means the probability of the occurrence in each trial, and size is equal to 10. Okay, which means return a 10 sized array of binomial values. Okay, what does each value in this mean? Let's understand. In the first experiment, which is this experiment, okay, let me first tell you, this will be the first experiment. Basically, when you see it as a list, it's 0, 1, 2, 3. Okay, that is how the indexing starts. Like in DSA questions, if you see, they will mention that it's a 1 based indexing or a 0 based indexing, and you have to code accordingly. But generally, it starts with 0, 1, 2. That is how the indexing of this list look like. But here, what is the first experiment? This is the first experiment, second, third experiment. In the first experiment, there were 6 successes heads out of 10 trials. That is what this number means. We are generating a random information based on the parameters here, right? Same way, second, we have got 8 successes out of 10 trials. In the third experiment, we have got 2 successes out of success. Nothing means head. Okay, that is what the values in this particular list means. Next is SNS.distplot. Random.binomial. Basically, I am plotting the same to see the data. You could see the bar chart here where it represents the actual values from the output array. Okay, next is what is the difference between normal and binomial. Okay, if there are enough data points, it will be quite similar to normal distribution with certain LOC and scale. What is LOC and scale? With a specific mean and with a specific scale, and if we have a good number of data points, it will be more or less equal or similar. That was what they are telling here. If you see here, okay, so I have given LOC 55. You could see the parameters that you had given here, and finally when I have plotted this graph, both the normal and the binomial looks similar in terms of the graph representation. That is what they mean. When there is enough data point and for a certain mean and a standard deviation value, it would look similar is what that they mean. Next is Poisson distribution. Estimates how many times an event can occur in a specific time. For example, there is a call center. Okay, the Poisson distribution model the number of incoming calls per minute, where lambda represents average rate of the call. For example, there is some 1 hour time duration and this call center has some X number of calls. That is what this X is, what the actual average X should be an average value of the calls that you received in that 1 hour. Okay, so lambda is the average rate. Let's assume that to be 5 here. Okay, so lambda is equal to 5 and size is once again the return result that you need to have, where there will be 5 values that is mentioned. The generated value stored in variable X represents the number of incoming calls that occurred in that minute. Okay, and these values, okay, variable number of incoming calls occurred in that minute based on the Poisson distribution with the average rate of 5 calls per minute. Okay, that is understanding the output 35174. What does this mean? Okay, by applying this, what does this mean? 3 means that in one particular observation or one specific interval of time, there were 3 occurrences of the event, which means there are 3 calls in a minute, 3 accidents in an hour. Okay, 3 accidents, okay, something like that. Three events happened in that particular duration is what this 3 means. Next is 5 indicates that the another observation or interval there were 5 occurrences of the event. Okay, next is there were 1 occurrence, 7 occurrence, 4 occurrence. That is what this particular output means like, and this is how you apply the Poisson distribution. Okay, so as of now, what all we have seen, the first thing is we have seen the normal distribution. What does the normal distribution mean like? It means the bell-shaped curve. Okay, the parameters are the standard deviation and the mean. Next is what we have seen, discrete values, which are this, and continuous values distribution, which are actually some kind of a temperature or a weight. It is continuous. And next we have seen something like a binomial, which means there are only 2 occurrences, either tail or heads. And the next thing that we have seen till now is next is Poisson distribution, which is like how many events can occur in a specific time duration. Okay, next is normal versus Poisson. Okay, similar to binomial, for larger Poisson distributions, what do they mean by larger Poisson distribution? For a lambda value of 50, which is an average value, it will become similar to the normal distribution with certain standard deviation and mean. That is what they mean here. If you see here, we can see that the similarity between the normal distribution and the Poisson distribution as well. It looks much similar, right? So it all depends on the values that you put for Poisson distribution here. Next is uniform distribution, describing the probability where every event can occur has equal chances of occurring. Okay, for example, while tossing a coin, it means that the possibility of getting a tail and the possibility of getting a head is very closely like 0.5. It is very equal, right? The event of both of these events happening is very same, right? Which means A is equal to lower bound, B is equal to upper bound, and size is equal to the shape of the written array. As we see here, we are expecting a 2 into 3 matrix as an output. We are applying this uniform distribution where these are all the values that you are getting. What does this value actually represent? Each value in the output array X represents a randomly generated number drawn from a uniform distribution within a range of 0 to 1. Okay, that is what the values here means like. Next is, if I plot this, this is what we get. Next is logistic distribution, used to describe the growth. Okay, logistic and normal distribution are more or less identical. It helps us to understand the actual growth. Okay, if you see here, there are parameters like LOC. Always LOC means mean here, and where the peak it is by default it will be 0. Okay, mean. Next is scale, which is actually the standard deviation, and the size, the returned array size. So these are all the parameters that is given to the logistic regression, and we have used the logistic function here, and we have got the values here. What does they represent? So we have got these values from the logistic distribution with location parameter of 1 and a scale of a parameter of 2. Location means mean parameter of 1 and standard deviation parameter of 2. These are all the values. What is the practical use case? For example, how fast the YouTube channel is growing, and definitely I need your support, guys. Please subscribe to this channel. So that is where you get to understand this actually. The growth of the thing is also this is much used in the data science, all those industries as well. Okay, if I just plot a simple graph, this is what you get. Next is multinomial distribution. Outcome of multinomial scenarios, unlike binomial where scenarios must be one of the two. You toss a coin and you get tail or what do you say, tail or head. Okay, so which means like this is only two occurrence. But in multinomial, take an example of a blood type. So a person has a positive, that another person has a B positive, another person has AB. So there are multiple types where that is what I mean by multinomial distribution. Outcome of multinomial scenario like binomial, where scenarios must be only one of the two. Okay, binomial is one of the two, but multinomial is multiple. Okay, so same way, n number of possible outcomes for each 6 dice roll. I'm making a 6 dice roll. What would be the possible outcome? Somewhere between 1 to 6, right? Also, next is p value, list of probabilities of outcome, which means I have 1 by 6. What do I want? If I make one experiment, okay, assume that I am making one single experiment, okay, and in this experiment, I am going to I'm going to toss a coin. What is the probability of getting a head or a tail? I'm going to roll a dice, which means there are 6 numbers in a dice, and I would definitely get one among them, right? That is the possibility of getting it. So 1 by 6 is the probability. So that is what I have defined here as probabilities of the outcome values, and totally 6 possible outcomes are possible. Okay, that is what n parameter means. Like, and what does these numbers mean? Outcome 1 occurred only one time, outcome 2 occurred only one time, same way outcome 3 occurred only 2 times. Okay, that is what it means like. Next is exponential distribution, which describes the time till next event of failure or successes, like scale inverse of rate. See lambda in Poisson distribution. What does lambda in Poisson distribution means? Like when there is a call time coming in a specific duration of a time, what is the average rate of the number of calls was the calculation with this lambda, right? So scale parameter is the inverse of the rate of the actual thing happening. For example, something assume this. Okay, this is what is they mean like. Next is I'm giving the exponential scale. You know, it is a it is standard deviation, and you get the values here. What does each value represent? They represent a random observation drawn from exponential distribution with a scale parameter of with a standard deviation of 2. These values represent durations or intervals between consecutive events. There are consecutive events happening, and these values represents those durations of those consecutive events, where the likelihood of observing shorter interval increases as the intervals become smaller. Okay, next is these are all the other set of things, like from chi-square distribution, Rayleigh distribution, or not Pareto. It's actually a law, right? So these are all the other kind of distributions that are actually present. I will share this actual Jupyter notebook with you on GitHub. You can go look into the video link, video description to get this link, and you can go edit this or whatever you want. I have also given it both in the PDF format and the Jupyter notebook format to you for you to execute. Okay, so I will just give a brief on what it is. Okay, next is chi-square distribution, not very familiarly used. What is a hypothesis? Okay, so basic to verify a hypothesis. Okay, so what is meant by a hypothesis that you need to understand? Okay, so something that is not actually proven, but that is how it could have been. Okay, that is what hypothesis is. So if I have to take an example, okay, checking if the number of red, green and blue candies in the bag matched with what was expected. Okay, so I know there is a bag. Okay, I know there is a bag, and there are balls red, green and blue, and I'm telling that I guess there will be some X number of red balls, Y number of blue balls, and Y number of Z number of green balls. Okay, so this is an simple expectation I have. Okay, so this is not a proven thing, but maybe there are chances that the bag also has the same number of things as I predicted. It is not a prediction as well. It is something that I thought within myself, that could be the count of the numbers of the balls that is present within the uh, bag. Okay, so it becomes hypothesis. It is not a proven thing that this is the count of each ball, but that could be the case. That is what a hypothesis means. Like, so this chi-square distribution is helpful to verify such kind of hypotheses. Okay, how do you implement them? Df, which means the degree of freedom, psi is the actual written thing, chi-square, same way random dot chi-square, you just implement it. And what is, these are all the values that you get out of a chi-square distribution. If you want to learn more about this kind of distributions, go refer to Google, because there are a lot of proof concepts or equations that I have to write down to actually explain it, but in real time cases that you don't need them actually. Okay, it will be something like a proof of a theorem, all the things. Okay, next is Rayleigh distribution, used in signal processing to model signal amplitudes in scenarios like communication noise or radar signal reflections. Okay, used in signal processing to model signal amplitudes in scenarios like communication noise or radar signal reflections. Okay, Rayleigh scale, which is standard deviation is 2 and the return is 2 into 3 matrix. Okay, we got a result here. Next is Pareto distribution. I think most would be familiar with this Pareto's law, which is that 80-20 distribution. 20% factors cause 80% of the results. Okay, that is what it means, outcome, as what is mentioned here. Models the distribution of the wealth, where small percentage of the population holds the majority of the wealth. For example, if you take India, the richest people in the country hold, the count of the richest people in the country is very small, but they hold the majority of the wealth, right? So that is what it means, like models the distribution of the wealth, such as distribution of income among the individuals, all of them. Okay, next is this is how you apply this particular Pareto function as well. Next is Zipf distribution, is observed in phenomenon where the frequency of the occurrence of certain event follows a power law distribution, such as distribution of words frequencies in natural language English, where few words occur very frequently while most words occur very rarely. For example, if you take these stop words and all, like in and what, all the stop words, what happens is they occur very frequently, because these are all like general conjunctions that we use when we talk in English to actually complete a sentence, right? So in that case, these occurrences will be very high, but actual technical values, because in the whole lecture, if you see, I have spoke about this Zipf distribution only once, which means it occurs only once and it's very rare to see. Okay, so that is where the Zipf distribution helps us to observe the phenomenon where the frequency of the occurrence of the certain events follow a power law distribution, is what we mean by that. Okay, same way you have this parameter A, which is actually the distribution parameter, and expecting a 2 into 3 matrix. Okay, so A is equal to 2. Fine. So that is all about the NumPy, and this is how you have to implement all the statistics. Basically, you put a random and just call the type of distribution that you want to perform, and you get the actual stuff. Okay, so I have completed the basics of Python, which includes list and all the typical data structures, loops, if-else statements is all completed on the first lecture. Second lecture, I have spoke about the NumPy. Basically, I have spoke much on the arrays operations and how do you do some general operations. Next is, in this lecture, I have completed covered the statistic version of the NumPy, and next is we have pandas and matplotlib, and basically that will be the final lecture where I will be covering the functions of pandas and matplotlib. So this pandas and matplotlib, basically use matplotlib as we seen here. We are just going to use it for plotting the graph, and pandas we are going to actually load some data, read them, how do you index them to analyze the specific data. That is what we are going to do with pandas. Okay, so the next lecture would be of one lecture combining both pandas and distribution. So also after completing this, I want to do a complete full-fledged data analysis with Python. Yeah, development is there, I totally understand, But with development, here we are going to write some simple functions and get things done. But when it's a development and you have to do it properly, we have to cover OOPS completely. The object-oriented programming principles. I have to complete it, fully finish how to implement a class and how do I modularize the code, how do I run things in multiple threads. I have to discuss all of them. So for in the specific playlist, we are not going to concentrate them. First, I wanted to actually go and explain what OOPS is, each and every concept is, with some other programming languages like C++, so that it becomes much clear when you come to Python. Also, you will have a lot of keywords with respect to C++ and with respect to OOPS in case of C++. Okay, so the plan that I have is to actually do some data analysis. Let's see if you have some ideas, please comment down on your ideas, that and I will pick some data related to the things that you let it be something real time and real world data sets that we are going to analyze, so that people, everyone, whoever looks at this lecture, have some understanding on, gets an insight along with their learning. Okay, so comment them. Also, see you in the next video. Thank you so much.